you will be leaving for 6 months.
Yes.
6 months. She will be leaving, but before she will tell us everything about photorelay, dark matter, and luminous matter with neural networks. Please.
Is this the collection? Because there's so many. Come back. Okay. Okay, so this work that I'm gonna present today, I've been doing in collaboration with people from the Institute of the Canary Islands, which is the Institute for Astrophysics in the Canary Islands, which is the place that I did my internship abroad. And well, the idea is to study and model yellow bias using a neural network. So let me start giving some context to base this work. Well, so here we're talking about structure formation and large-scale structure, right? So we start like from some initial density fluctuations, which eventually will evolve into gravitational interaction form the structures that we observe today with this pattern, this cosmic web like of
What is this happening?
And well, and the overdense, the regions, the overdense regions with higher density may eventually collapse to form dark matter halos, which are these gravitationally stable, like visualized structures, and eventually then galaxies may form inside these dark matter halos. So I'm just saying all of this to give like to try to really give like the big picture where this work fits in. So, and because eventually this work will be relevant to connect everything that we learn, like from starting from initial conditions and evolving and getting our dark matter density field with observations, which are the galaxies. So the dark matter halos play a key role in this full like pipeline, this full modeling of the structure formation.
Sorry, in the previous picture, in the previous slide, can you see the dark matter halos in that picture?
Well, they should be like this in more over dense regions, because here we see like the filaments and the knots, and also the halos, they are in this region of more concentrated matter, which here is represented in the light colors. But it's not, this is just to show that the large scale structure picture. Here I have like a cartoon illustrating like a halo. But just to say that what I'm talking about here is like a dark matter halo, which has typically a central galaxy, a very massive galaxy, and also subhalos with satellite galaxies hosted by the subhalos, right? Okay, so yeah, so then as I said, we have some model to obtain the dark matter density for the distribution of dark matter. We may find the halos there, and then later we can apply some prescription to populate these halos with galaxies, right? And this is like the galaxy connection. And what I'm going to talk about today is more like this relationship between the dark matter density field and the halos and the distribution of the halos. This is what we call the halo bias, because the distribution of the halo, this relationship between the statistical distribution of dark matter and the distribution of the halos, it's what we call the halo bias, right? And so this is just to give like a very big picture, very broad explanation to see how this will, why this piece of work is important to eventually connect with observations. But now let me be a bit more specific in my motivation here. So when we study like cosmology, large-scale structure with surveys, with cosmological surveys, we need what we call mocks for large-scale structure. So, which is like a mock, meaning like we have to mimic, like to simulate our observed universe, okay? And for example, we could use like n-body simulations because we have initial conditions and we can evolve them using some equations. But these are really expensive and we need to cover a very large volume in order to apply this to this service. And the idea is that you have to do like many of these fast simulations because we need many realizations of the universe to characterize the physical process, the statistical processes of the generated our observed universe. So eventually, and then we get the observations and we can, using our models, we can infer the initial conditions and constrain cosmology. But the message here is that we need like these fast simulations of very large volumes, and we need many of them. So doing like n-body, things like n-body simulations is unfeasible. So we rely on what we call like approximate dark matter density field. You may use some gravity solver and obtain a dark matter distribution.
So what do you mean gravity solver, numerical solver or just approximate?
Approximate, yes, and I'm gonna explain which one we are using here. So yeah, so this will be like accurate. Accurate with respect to the compared to the embodied dark matter density field in some scales, in some limits, but the challenge, yes, this is part of the challenge because we rely on this approximate dark matter density fields, and the one that we are going to use in this work, the one that we are using in this work is it's called augmented Lagrangian perturbation theory. So let me start. So on very large scale, we can rely on what we call Lagrangian perturbation theory. And the idea is that the gravitational resolution is encoded in a displacement field here. So you start like for some initial positions, and you can simulate the gravitational evolution of the particles with this displacement field, okay? And this is accurate up to some scale, and you can model this displacement field like you can go to first order, second order, it depends. Here we are going to use like second order Lagrangian perturbation theory to compute the displacement field to model the large scales. But then we know that this is only precise up to some scale, and that so the idea of the ALPT, the augmented Lagrangian perturbation theory, is to combine this displacement field that models the larger scales with another one to model smaller scales. And this displacement field is to model like the spherical collapse, to model like the realization towards small scales. Of course, this is still an approximation, okay, but this is just to explain what I'm using. And then you combine like these two displacement fields with a kernel. This is just like a Gaussian filter, which is a function of some smoothing radius. You can choose to balance the contribution between both. This is typically like 6 megaparsecs. You can choose, you have like, you can like, for example, fit this smoothing radius, like seeing the correlation between this approximate dark matter density field with the one for the n-body simulation and optimize that to choose smoothing radius. So, yeah, so yeah, the takeaway message here is just that we're going to use like this approximate density field. Okay. Now, okay, yes. Yeah, before that, let me just explain. So when you have an n-body simulation, you get a distribution of dark matter particles at a certain redshift, and you run like what is called like a halo finder to find the halo. So then with an n-body simulation, you will have the positions of the dark matter particles and also the position of the halos. Okay.
Usually, dark matter particles are they are the same.
Yes, but it depends on how you define a halo. And you
Yeah, you must have a threshold over density.
yes, yes, there's you have the threshold over density, but I think there are many additional things that you do. It depends on the halo finder. We use like friends of friends or more complicated methods. But the thing is that once you find, once you have your dark matter distribution and your halo distribution, we know that the relationship between them is biased.
So the halo must be realized. It's a realized concentration of that matter.
Yes, yes.
In the case of the short range interaction, so the spherical collapse, of course, it would apply to all the regions where halos form. But this is like a field approach to having that. So I guess that you would, I mean, you have the kernel that it's regulating where the transition occurs, but it would occur in all the points, including all the places where you also don't have halos. So what I don't fully understand is that I understand that for regions in which you would have spherical collapse, that small scale correction would include more like would be more precise. But applying that to all the advections on the Lagrangian space, I'm not sure how it would affect for, let's say, voids. Or maybe it would just displace them out. I don't know. I want to understand a little bit better how this spherical collapse correction also applies or has some gain outside halos. Because I would bet that
I think this is applied everywhere. But I never thought about that.
but that's on like on the paper where they develop this out.
Yes, yes. I have like in the extra slides, I have like the analytical expression for this. Aspect.
Okay.
Yes, then we can check, but they explain it, yes. But as far as I know, they apply this everywhere, regardless of the region that you are. Well, these people, whenever they use this kind of things, they take into account the cosmic web, but it is later, so it's different images.
Are fingers of God included in this description?
I don't think so.
I'm sure. I guess that yes. I mean, if you're because that would appear when you then measure afterwards with respect to the velocities of the things that you have there. So it would appear as something that you measure from that field.
So it's not modeled.
I mean, it's more when you take the observations, no? I mean, this is like field level and figures of God here when you measure in redshift space. So it's a redshift space feature, not a Lagrangian or a Euclidean space. That's coordinate space.
Yeah, that's okay.
Okay, so now this is more practical, just to explain how things will work. So we represent the dark matter particles positions and the halo positions in a grid, like this three-dimensional grid. This is just a slice to illustrate. The slide to take one of the slices of this cube here and plot. And then you see the structures here. So yes, and then each of these cells, the boxes here, like the 3D pixels in this box, it's I refer to this like a definite volume here, like a box like this, okay? So then you have the halos and you represent them in the grid. And then so this is just to explain like the pipeline. So we take like an n-body simulation. It has initial conditions, which has been evolved with the body solid. Then it runs like a halo fiber. So we have our dark matter density from the n-body simulation and our halos position, which we can represent in a grid like that and compute like the dark matter field, the halo fields. But we can also take these initial conditions and run our approximate dark matter, our gravity solver, and compute the approximate dark matter density field. And then the idea here is that we want to generate like a halo density field based on this approximate dark matter field. Okay, and then I need some model to do that, like to do this mapping between the dark matter field and the halo field. And for that, yes, so as the title says, I'm going to explore the neural networks and things like that. So that's what I'm going to talk about next. But the idea is that I want my halo density field, my mock halo catalog, right, to be to resemble the n-body halo field, at least like in some statistics. So like the abundance, I want to predict the correct number of halos. I want to make them their 2-point correlations accurate with the power spectrum and the bispectrum, and it depends on how accurate you have to be. So the n-body simulation that I'm using is it's called UnitSim. My box has 1 megaparsec over each side. Okay, so it's and 256 cells, which means that the resolution, like each of these boxes here, has a resolution of 4 megaparsec over H approximately. So this is very low resolution, you see, right? And yes, and spreadsheet 1. Okay. Right. So the way we're doing this now is the following. So in order to build my halo density field, I want to predict the number of halos in each of these cells, in each of these boxes. Okay. And then I do like for each one, and then I build the grid again. Yeah, you see, this is, of course, this is all okay, because here there are 256 cells, and this is just to illustrate. If I take a single voxel from my box, this is represented here, and I can do the same with the dark matter density box. And then so on the one hand, I have the dark matter density in this voxel and the halo density in this voxel. I want to use this information to obtain the density of halos in this volume. Okay, and how we can do this? So the most like the simplest assumption that you can make is that this density of halos is like an expansion, like in powers of the local dark matter density. Okay, this is called, like in the literature, people often call this like the local bias because you're simply using the local density. But yeah, a more precise, maybe more precise nomenclature is to call this the local matter density bias relation. Okay, but this does not tell the whole story because this distribution, it doesn't depend only on this local density. You have to account like for larger scales contribution of the environment, and that you can model using, for example, the tidal field tensor, which is the hashing of the gravitational potential. Okay, so so the question is, what can the halo density depend on? There is a huge literature on that, on halo bias, right? Here based on a few works. But yes, so if you have questions, because the nomenclature sometimes is mixed. Okay, so so you see what we are trying to model. So in this here, it's delta TR is for tracer and toolkit for somewhere another. But you can just see this like it's the halo density, right? And then we are going to model this as a probability distribution for the density or the number of halos in that small volume, that voxel, conditioned to a set of features that you extract from your dark matter density field. And why is that? Because, and this is, we do this way because if you had like only a function, this is not exactly a function because there is a stochastic component, right? So if you model like a probability distribution, you can account for this a lack of knowledge, like this is statistical contribution, stochastic contribution. Here I'm just defining the tidal field, like the action of the gravitational potential. And also you can, yes, so you could also explore what is here they call the short range for local bias, because here you're using like the gravitational potential, but we could also do like something similar with the density itself, okay, and see the contributions of adding this to our model.
That's gonna be higher order. Mm,
Yes, I agree. Yes. So because here, if you take like so because here this the traits will be like the Laplacian. This is higher.
But you're truncating this particular, it's like an expansion and then you're truncating at some order.
Yeah, so so these quantities, yeah, I'm gonna, because I think this here it's better to discuss this. So because some of these quantities, so when people do this with analytic expansion, they, well, at least the paper that I'm using, they stop at third order and claim that this is enough to model large scale bias. Okay?
Yeah, indeed, I was going to ask why not derivative? Not why you include derivative in that Taylor expansion?
Yes, you can
Yeah, I see that you're adding now. Yeah.
This is just a few more definitions. Okay, so you can define like this tensor here, which is like this the traceless version of the tidal field, and compute scalar quantities because our density is a scalar quantity. So you compute scalar quantities from these tensors here. Here's the equivalent for now for the you see, like here's delta, but it's actually the Laplacian of the gravitational potential Poisson equation, right? And here is the analogous to the density. Okay. And then, well, and these quantities, you can also, can compute like these quantities like S2, S3, these contractions of these tensors with invariance of the tidal field tensor. Okay, so you compute the eigenvalues of the tidal field tensor, and you can generate like these invariance quantities, which are combinations of the eigenvalues. Okay, I'm not showing here like how exactly to combine and to obtain the quantities, but you can do that. There are some works showing this. And this, yes, it would be important for a later discussion. So I wanted to comment on this at this point. Okay. Yeah, so as I said, right, so, okay, so what I'm gonna try to do now is to model this probability distribution with a machine learning model, okay? And so let me explain how it works. So let's start with the usual, this is like I think it's the simplest neural network, the fully connected multilayer perceptron neural network, right? So usually what we do is we have, so yes, this kind of network, if you have like an infinite number of hidden zeros here, like units, it can approximate any function, okay? So the idea is that you have a neural network to approximate a function. F of x is y, and in our case, x would be the dark matter density and these additional features that we discussed. And y, our target, is the number of halos in the volume, okay? Well, so then in our usual neural network, you would input the input features like from the dark matter density field and have a model that would produce an estimate for the halo density in that volume. And yes, and the idea is that you optimize these parameters, like you have these weights, like you weight each of the features and you optimize these weights using by minimizing a loss function. Okay.
So the parameters that you find or by this optimization are the coefficients of the power expansion.
Yes, in the end it would be that, yes. Because yes, so you start when multiply, so the first weight, the first parameters multiply like the density and the S2, it depends on what I add here. And then you perform a series of combinations and nonlinear transformation to approximate a function with a very general shape. But yes.
So the input is the density contrast in dark matter in each box or in each,
In each of these small volumes.
so there are 256.
Yes, but what I'm doing, so. Yes,
Yeah.
it's a small volume here, right? And. But this is important because what I'm doing here is I am treating each of these boxes like as an independent thing. It's my training instance, you know? It's like a pair, an independent pair, and I'm trying to model this way and then rebuild. If there's, because I don't want to advance like this discussion, but this is what I'm doing. Yes, I have like for each of the pairs, so I have a bunch of, I have 256
Box.
cube. Yeah, so I have.
Sorry.
Yes, because it's per dimension, so I have like 16 million boxes to train and validate and do. So what?
That's for dark matter. So the output is the same thing in the same boxes, but for halos.
Yes, yes.
So the output is also this huge dimensional thing.
No, the output for the network is a single number
For each one.
for, yes, for each of the.
Yeah.
Yes.
So it's a.
But once I rebuild the grid, I will, I have to run my network like for each of these instances, like 16 million times. Is that clear? It's not like my output, the output of the network is very simple. It's just a number because it's the density in this, in
The
this.
number.
box. Yes, the number of variables, number, yes.
Yeah, but still you have a huge number of boxes.
Yes, I have, yes, but it's not like I'm trying to predict all of them jointly. You know,
It's just one box.
It's just one per time to fit the network.
And in the input then, it's not just one single value for the dark matter, it's the different fields that you have there, no? So the tidal,
Yes,
the value of the dark matter, smooth scale.
yes, it's this quantities. It's S2, S3, sorry.
Mhm.
But this one is better discussed there.
So you train one box cell at a time.
Yes, yes. It's because one thing that I could do, such as one thing that I could do would be to predict all of these jointly. Then this would be a much complicated problem. Yes, because my output of the network was like many numbers. I'm not doing that. I'm doing
One box of the.
Yes, but I'm somehow assuming that these are independent.
So you have a huge number of neural networks.
Yes, it's a single neural network, which I'm gonna input the density for each of the boxes to
Ah,
then build.
yes. So I have to run this neural network.
Yes, many times, but it's fast.
Yes,
That's the. That's the thing. Yes.
I don't know if it's a naive question, but they have a reason for these 256 boxes because you say obviously the result will be a large number, but you said this is a very low resolution. So you choose this number like with a reason, with because taking consider the computational cost, or it's just a
Yes,
assumption.
I'll say that because when you think about producing blocks, they have like bigger boxes, and you cannot have like a super high resolution because once you do this approximate gravity, dark matter, this approximate dark matter density, you want to do this many times. So if you have too small too small number of cells to high resolution, this will be super expensive. Yes, because here I already have like 16 million cells. If I reduce the resolution, if I increase the number, this will be like super heavy computationally, like to store it. I think that this is the main reason is for this computational limitation that you have.
Also, if you fill the box, then you will end up with many boxes with zero halos, no? Because this size is 4 megaparsec, you said?
Yes,
So in 4 megaparsec, you expect a handful of halos.
yes, there
So-
are many, but there are, it's also true, there are some boxes which. have-
Yeah. Exactly. I mean, you don't expect hundreds of halos in 4 megaparsec, you expect 10, I mean, no more than 10-ish.
Yes, yes,
So if you make it too much smaller, then most of them will have zero.
yes, that's true. This affect the distribution, but yes, that's true. But this is something that it would be like, let's say, my problem, you know, because there's so that this decision is a prior choice. It's, but that's also true. That's irrelevant actually, because this will affect the distribution per cell. Yes. So it's in, yeah, so I'm. This sense, this is very simple. This is not like a super complicated network that I have to output a really high dimension. We're starting from there because we want to see if we can model this using only local quantities, quantities that you can compute locally here. And but yes, but one important point is this is kind of arbitrary. Okay, I'm just accepting. But this is somehow an arbitrary choice. Maybe I could improve, I don't know. But I'm just trying to handle the problem as they pose me due to these challenges regarding loss and. Okay, so yeah, so I'm gonna start showing the results, but before, I just want to comment that we did like a kind of a sanity check. So for this slide, forget about the n-body halos. We took the dark matter density field and we generate our halos with a simplified model. Okay, and then we try to reproduce this generated halos with the neural network. And this is a simple model because here our bias model is just a function of the total density. So I just take this density and then do like 1 plus delta to alpha. I can choose alpha, okay? So this is a model, a bias model that I understand very well. And I know that it depends only on the local density. And then, yes, and then you do that and you generate you compute these parameters that the rate parameter in a Poisson distribution. So if you define your bias model and you do a Poisson distribution on top of that to generate your simplified halo catalog. This again, this is just an exercise for sanity check of the methodology, okay? And then this is just to say that in this case, the method works very well. So these are two types of neural network. And remember, I'm only fitting this. And because the dependency is very clear and it is accounted in for sure it's accounted in the neural network, I can reproduce very well like the abundance of halos and also the correlations higher order statistics. This is a power spectrum and this is a configuration of bias spectrum. By the way, what is this one that we use? Wait, this how that like this, okay? Because yeah, you can compute like many configurations of the bias spectrum. You're only looking like this one because
Age of the dragon parse.
yes, I think so. But what I just to see the configuration of the triangle is this one that we chose. And yeah, so the idea is that by simply fitting this very like straightforward relation, in principle, you would obtain and everything well correlated here. And I forgot to, because I didn't explain very well the thing with the neural network. So usually in a neural network, you would have, you use this like to perform a regression, meaning that your loss function is like a mean squared error or something. But the point is that you are predicting a single value, the expected value. But in our case, since we want to model like a probability distribution, we want to capture this uncertainty. Actually, what we do is to use is to predict the parameters of a distribution here, right? So you can choose like a parametric distribution, just as an example, like a Gaussian, Poisson, binomial, whatever. And then the output of your network will be the parameters of this distribution. So for example, on a Gaussian distribution, it would be like a univariate would be only the mean and the standard deviation. So the output of my multi-layer perceptron would be 2 neurons. I use them to compute my Gaussian distribution. Then I get my target value, the value that I want to reproduce, and see how likely it is that I observe that value according to that distribution. And I want to maximize this likelihood, in other words, minimize the negative log likelihood, okay? I'm saying this just to give like an idea of how these things work. This is how you do with a parametric distribution. But there are many more refined models that you actually don't parameterize. You have much freedom to model your distribution with different shapes. But the results that I'm going to show here today, what I'm using is actually a categorical distribution, which in the end of the day is a classification simply. Okay, so this is just the typical loss function for a classification problem. And the reason for that is because it's like you have like your distribution of tables here, something like this. When you like this categorization, this is what you're doing here. So you're kind of approximating a distribution with a very flexible shape.
What's on the vertical axis?
It would be like the number of cells with, so for example, I have, I don't know, 10 to the 7 voxels without any halos, then I don't know, maybe 1,000 with 10 halos. That's what I mean? Okay, so it's the number of cells in my box, on voxels in my box, which has the range of number of halos. So it's the occupation. So like, for example, I may have, like in this single voxel, I may have no halo, 1 halo, 2 halos. That's what okay?
It is a probabilistic result.
Yeah, this is just, you can just take your halo density field, your grid, and compute a histogram.
When I'm a bit confused, you have this 256 cells. I would have guessed that the output
By the way, it's 266.
56
256 cube, yes.
cubes. Yes.
So it's a lot.
Yes. I would have guessed that at the end you would find an output. What is number of halos in each of these cubic cells?
Yes, yes. And this is and once I get all of them, I compute the histogram. But what you say is correct. I want you to tell the number of halos in each of them. Once I have all of them, the 256 cube, I compute the histogram. That's the abundance. But it's also true that for each of the voxels, I will have a probability distribution. That's what I'm trying to model, right? So for this, here I'm talking about this single one. What my network is doing is to predict the probability distribution for the number of halos in this volume here. So I will have something like this. So I don't know. So the density here is close to 0. I don't know. This is the value for S2, and then I know what is the possible range of halos that I have in this volume.
Wait, so then in your out, I thought that you were using like a cross entropy loss. And in that case, the output of the network will be the probability, just a single number for each class, which will be a number of halos. But are you doing that or like,
It's a probability for each number, each class,
okay.
meaning that I have a probability for each thing, you know? It's like
Okay, so
infinite.
it's not, okay, so the output is not that it's giving you like the mean and variance. You are just taking it like a classification and the PDF is coming from the probability at each class.
Yes.
Okay, okay.
Yes, so what I said that it's true that this is a number, because once I sample from my distribution, it's a number, but the way that I'm parameterizing this distribution, actually, I would have, I don't know, 12 parameters, because the categorical distribution has, if you have 12 classes, you have 12 parameters. And I'm doing this way so first, because this is like a simple way to model something with a flexible shape. It has problems, it can be improved, but for the moment, that's what I'm showing here. And because I have discrete numbers, because really here, I'm talking about density, but the background, I'm really predicting like integer numbers. Okay, so
I mean, I guess it's interesting to check maybe how it changes with cosmology, no? Because you're learning somehow well, it's not the abundance mass function or something like that, the occupation. But I guess that, I mean, since there are different regions, maybe sigma-8, it's learning somehow depends on sigma-8,
yes,
but it's like still fixed cosmology, so.
yes, so this is a super next step thing, because that fixed cosmology, redshift, resolution, there are so many things. I'm just trying to investigate these contributions. And again, this is like part of a bigger work. There are many other methods in their group that they do like something similar. So the idea here is to give some insights to the other models. But I agree. And the other thing is I have to be careful, because as I said, I take from a single box, gigaparts cube box, some of the cells to model. But if I take all the cells and avoid, you know, I have to be careful from where I'm taking. I don't want to bias, you know.
Maybe you can use the unit sim 2 because they had 2 simulations with fixed pair. So maybe you have
Yes.
other 3 boxes to validate.
Yes, my plan was to pick like, that's, you know, I'm also changing simulation because of
Okay.
that. But my plan was like just first try to do this in a single one and then change the initial condition, see how it generalizes, because there are many other things that should be checked here. But for the moment, I'm only using like, trying to do thing with the single balls.
And that's just a very quick question. So how many simulations you have in the training set?
It's just one.
Just one.
It's just, yes. But this simulation, it has like 2 runs, but then it's fixed and pair, so you have the opposite phase in the end, and check is of course. So I said all of that just to give like this bigger explanation of this idea of modeling probability distribution, but in the end of the day, I'm doing a classification here, okay? Just want to put this in this bigger picture, because I also compare different distributions, like this is where I started, right? So for instance, here, I'm using like a Poisson distribution and comparing, because it is, I use a Poisson distribution, it's the story exam, okay? With this classifier thing. Yeah, but this is just a sanity check, just to comment. Okay, and now back to the real task. So now, after doing this, so here the different colors are different inputs. So I start only with the local density, and unfortunately, I don't think you can see anything. I'm sorry about that. But there is like, when you input only the local density, you have like this huge bias in the power spectrum on large scales. And then I try to include this additional information to see how things improve. So I'm just.
So the local density with all that expansion with the quadratic, cubic.
Yes, so the green one, first one is only the local density, then this light blue, I do like S2, this term which is computed with the tidal field, the tidal field. And then I try to add more information and see how this translates to higher order statistics, because hopefully I'll be modeling non-local bias. I'll have a more complete description of my halo bias model.
do you mean by the true curve? What do you mean by
Yeah,
that?
the true curve is the n-body thing, the halos from the n-body simulation. That's what I mean by true is my reference actually. So I'm trying to reproduce with my mock catalog the distribution of halos from the n-body simulation. And yes, and then when I compare, so as I add like these additional features, I could see like some improvement here in the power spectrum by adding, for instance, this term. But then everything looks similar. I can see some improvement in terms of other metrics, like correlation cell by cell, things improve a little bit, but in this statistics which are actually interesting for us, I don't see much improvement, but this is only growing world, okay, there's still, yeah. But this is one way to approach this problem. Another way that I want to comment is it's about using deep learning, about using convolutional neural networks, right? Because all that we did here now so far is computing these other dependencies by hand, like we extract the features ourselves. The concept of deep learning, at least the way that I like to think it, is that you let the machine do the feature extraction. So you just give the input the raw data, which is the dark matter density field, and let the network learn whatever is relevant to perform our test, which in this case is like the loss function is this mapping between the boxes, okay? So since this is like a regular grid, it makes sense to use a convolution neural network, which is used for images, but you can also do this in 3 dimensions, which is our case, like this box. And yeah, so this is just to illustrate. Again, we are still trying to predict the number of labels in this specific volume. But now I could, for example, use the information of the surrounding cells. All of them have a density associated, and I can, yes, and then I can use the neural network to extract some information, like to make some summaries value from this information of the surroundings, and then this would be. So this is just to illustrate the structure of a convolutional neural network. Okay, so this would be like this feature extraction stage. You do the convolution, and then once you perform this feature extraction, then the procedure is the same. You go with the NLP, but this is all at once. You feed like this weight for these kernels, these windows here, and the NLP all together, because the goal is to extract some features in order to optimize your loss function, which is computed with the output of your network. Yeah, this is just complementary, because yeah, we could find a better model. And yes, one more thing. So I'll show the results doing this, but in addition to that, something that we tried was to combine this with the information of the cosmic web, because as I said, you can, I said that you could compute those quantities here from the bias expansion with the eigenvalues of the tidal field tensor. And there is like a definition of the cosmic web classification. This is one definition. There are many, and it depends on your scientific interests. But one of them is based on doing this like these thresholds in the values of the eigenvalues. Okay, so you define like knots as all positive eigenvalues, filaments, sheets, and voids. But so now, once I do this, I know for each of these boxes, I know like the cosmic web type of cosmic web. And what I'm doing, and then Susan, I'm going to show you the last slide, is actually to train a different CNN for each of these cosmic web types. And so I have like 4 networks, one for each cosmic web types, and then extract the local information. And the argument for that is like, because it's that you really want to try somehow effectively account from the contribution, the non-local large scale contributions for light. When I do this, yes, sorry, this is just to illustrate my point, because this is the dark matter, the halo density versus the dark matter density, okay? And computed for each of these cosmic web regions. Right? So you see that there is some difference here, and there might be some information, because if you have a different model for each of these relations, you're somehow capturing another contribution. And because of this relation between the eigenvalues and these quantities, this is somehow effectively perhaps modeling the contributions predicted for perturbation theory. So there is like a relationship between this cosmic web classification and the terms from the perturbation theory bias. And then this is just to compare. So the purple line is this convolutional neural network, this combination, and the blue line is what we had like before. So we see that for the Bohr spectrum, the results are they are very good. They improve. Like these lines here are 5 and 1%, so it seems to be very accurate. However, when I see the bispectrum, it's much worse. So first, I do not rely on the because I don't know exactly what it's doing. It looks like it's missing something, some contribution to be modeled here. And then, so then the idea is that I have like these two complementary approaches to model this problem in this way. And this is the status of the work now. So just as a summary, yeah, so we've been investigating how to incorporate this relevant information to model the halo bias using the approximate dark matter density field. And the idea is to use machine learning as an auxiliary tool, because as I said, there are other people in the group with different methods and different approaches. And yes, I think, yes, that's it. I think it's enough for the time.
Have you tried also or intend on trying using maybe recurrent neural networks? Because maybe you can also include some conditioning, and like the output of neural network could help you kind of evolve and see.
So I didn't understand the beginning.
If you thought of trying to also include maybe recurrent neural networks, because I was thinking as a convolutional would be amazing for the grid that you have, so you can have all the output of the cells, but you could also include the output and kind of align the networks together, and the output will become the next input, and it maybe could help in the conditioning information. I don't know. An idea.
Well, the application that I know with recurrent would be to model like a sequence, because then you would be a conditioning. So I think that what you're saying is maybe to predict the next voxel, to use the information on the previous, like a sequence or something like that. Maybe, yes. There are several different things we could try, and but I didn't try. The only thing that I did was with the CNNs, yes.
How do you keep isotropy in this way? Because if you took some particular direction to the sequence, you are breaking the isotropy, right?
And you don't necessarily need to take into the direction, because all the inputs will be combined with the outputs. You can train in several different ways. You don't need to put a specific direction into them. The output will be a combination of all of them.
Yeah, but the output of one cell would contribute to the input of another cell, right? So it has some kind of term in your space.
Yeah, maybe.
Yeah, I don't.
You go back to the bispectrum. So in this case,
Bispectrum,
you're comparing to you're comparing to the simulation one, right? You're not assuming peer level to do the.
No, it's
So that's true. That's the one that extracts from the original simulation, and then you compare with the. I'm just curious because it looks like, so when you do for the neural network, the precision was better. You were replicating the bispectrum better than in this case. But it's, in this case, it looks like you're getting like, extra, information because you're considering the neighboring cells. And in that case, it's just like assuming it's just one cell and you don't look at anything else.
Yes, I mean, hopefully I'm somehow modeling, no, other contribution, not only the local density, because of this quantity.
Yeah.
But yes.
Curious.
Because I don't know I don't know, I'm still trying to understand what this, to be honest, but, I don't know what the CNN is doing, you know? So that's why I think that both approaches.
It's over predicting like filaments. That's like, you're saying from that, you're saying that you prefer, like you have more halos aligned.
Why filament? Sorry.
So for example, you have like the theta equals 0, then you're saying that you have a closed triangle. So it would be like the very squeezed configuration.
okay.
Right? But it's weird that in the other case, where you have this linear process, you have a much better bispection than the case where you get the neighboring cells.
So I had also a question related to this, but I think it's, so I guess that the performance in principle should be better with the convolutional one, theoretically, because one, it's not forcing to rely on specific expansion. It should be able to extract all the information that is there, no? And my question was, are you seeing that in your loss, you are getting better results at the count level? Because I think this is very tough to interpret. Like the thing that you're asking it is to get the counts right. And then these other things come in a non-trivial way from those maps. So are you seeing an improvement there?
As far as I remember, yes. So this, at least that is consistent. Because I would expect that too, but, I mean, we have consistent model, I would improve the loss and I would get everything better too, but that's not the case, and then that's what I'm trying to understand.
I guess that what's the mask cut that you're putting for the halos there? Are you putting some?
Should do that.
Okay, so they are like what, like 100 particles resolved, or something like that.
To remember.
Because these things, I guess that they are also very dependent on how reliably you can get halos of different masses, and it's very non-trivial not to disentangle the things.
Okay. So let's take the ladies. There's no lunch downstairs, so you can go wherever you want for lunch, but see back at the.
Bring more this in. So these things like like a clean way.
Yes.
That's good.
Have you eaten all of the
Yes.